Okay, let's start. Okay, we're going to 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 start. That's 4, I think. Okay, we're going to start. Okay, we're going to start. That's the 6 times I said it. That means you stop talking. I get that it takes a moment, but it shouldn't take that long. Okay, here we are from last time. We were swinging this ball around at 9.7 radians per second. And if we wanted to get theta in terms of t, meaning given any time time since the ball passed the 3 o'clock position, we wanted to know what the angle was. So this is called the angular speed. And we wanted to write an expression for theta in terms of t, the time since it passes the 3 o'clock position. So remember, what were our 3 criteria for defining a good variable? Remember this from the beginning? How do we define a variable well? 3 criteria. Specific, that was number 2. It's just, you got to have all the details. Has units on it, that was number 3. Yeah, if it was distance or time, we have a starting reference point. Yeah, so it has to be a quantity, not an object. So it's easy to fall, so what happens sometimes is you end up calling a variable an object rather than a quantity. So we want a quantity that's specifically defined and has units. So if we say t is the time elapsed since, since the ball passed or started from 3 o'clock position. Is that good? Do we do it? We need a unit, right? In seconds. Okay, so the time elapsed since the ball passed the 3 o'clock position in seconds, that's a well-defined variable. I'm telling you that we're going to twirl it at 9.7 radians per second, and so how can we write theta in terms of t? He wants 9.7 t. Yeah, we did that last time. And we said, if you're not sure, what can you do to develop a formula like that? Make a table. Make a table and say, okay, if t is 0, what's theta? If t is 2, what's theta? If t is 10, what's theta? And then you can work right in front of you before your eyes, see that pattern emerging. And you'll see that the number of radians is always 9.7 times however many seconds has gone by. That's what 9.7 radians per second means. Every second, it goes 9.7 radians. So in t seconds, it's going to go t times that many radians. T times 9.7 radians. Okay? And so then if we wanted to write the horizontal position of the ball to the right of the vertical diameter as a function of t, how would we do that? We want the horizontal position to the right of the vertical diameter in radius, in a fraction of a radius, as a function of time. So if I want horizontal position, it'll be cosine And what goes into cosine? What kind of quantity does cosine take? Right? What's our input quantity into cosine? Angle measure. But if our input of our function is t, then we need that angle measure as a function of t. So what is that? 9.7t. Because we know 9.7t is an angle measure, and that's what cosine receives. It receives angle measure and tells us vertical distance, or horizontal distance, right? So what's the output of h? What's the units of the output of h? So what are we measuring? Fraction of a radius length to the right of the vertical diameter. Okay, so then we said, we talked about period, right? So first of all, what is the meaning of period? Can you remember without looking at your notes? What is period? Yeah. Danny?
One full cycle that it would take for it to go 2 pi.
Okay, so it has to do with a full cycle. So is period a measure of the input? Is it a measure of the angle theta? Or is it a measure of output? Which is it? Is the period going to be an amount, a value that's a value of input or of angle in this case, or of output? It's input, okay? It's input, so it's the interval of input. Let's write it down here. Period. The interval of input. In our case, what quantity is that? The input quantity? Theta? In our h function? No, it's time. Time. So we want the interval of time that results in what? One full cycle. So we want one full cycle of output. So it's how much time needs to go by, how much of our horizontal axis quantity needs to go by so that we get one full cycle of output values. So with the interval of input that results in one full cycle of output values. So we're asking how much time needs to go by so that our cycle starts over. So how do we know that question? We can answer that question knowing what the period of just cosine is. All right, so we want this thing right here. If we want one full cycle of output values, then that thing right there is going to reach what value? What goes into cosine, so we know that the period of just cosine by itself is 2 pi. You make it once around the circle, once around the circle, and then starts over. So when this thing right there reaches 2 pi, what we want the amount of time t that will make that thing reach 2 pi. So we want how much time needs to go by so that this, our angle measure, reaches 2 pi. So how do I calculate that? So there's some amount of time, call it TP for period, such that that angle reaches, so that's a really important idea right there. How much time needs to go by so that 9.7t hits 2 pi? Then we know we'll have a full cycle of output values because this is the period of cosine in terms of angle measure. So TP is 0.6478. I'll go with 648. Okay, so let's label. So then once we get that period, so this is seconds on our x-axis. So maybe this is, are you all hypnotized now? Okay, so now that that's 0.648, so then when you have the period, so eventually we're going to be sketching these graphs, right? So I just gave you this graph. Eventually we're going to be sketching these. So you're going to find the period, and then in order to make the sketch, we want to break it up into 4 equal parts because we know one period, one cycle really has 4 parts because of the 4 quadrants of the circle. So we want to divide by, we could divide by 2, we could divide by 4. There's different ways to do it. So we'll just start by dividing by 4. What is 0.648 divided by 4? Or whatever number you got up here divided by 4.
1.62.
Someone else get that?
Yep.
So that's our first quarter period. And in this case, that's when that horizontal distance reaches 0. Where's the ball right now? Top of the circle. Horizontal distance is 0. Okay, so now you could multiply this by 2, or you could go back to this one and divide by 2. That will give us half a period. 0.324. And where's the ball now? At 0.324 seconds from time equals 0, where is the ball? At the bottom. It's at the bottom of the circle, right?
To the left.
No, what are we measuring on this? What are we measuring on this axis? This is measuring horizontal distance to the right of the vertical diameter. So at 0.324, the far left side of the circle. You got to make sure you understand that. We're at the far left side because this is cosine. It's measuring horizontal distance on the vertical axis of our graph. So when we have a negative cosine value, or this is a negative then distance to the right, meaning to the left. So we're right here right now. Okay, then to get this, you could take 3/4 of that, or you could add these two together, right? You have half plus a quarter, however you want to do it. And what is it?
486.
486. And so now, if we were sketching this curve from scratch, these 4 numbers would be helpful to get us the 4 parts of the cycle. Okay, any questions? So that's kind of an overview of where we left off last time. Anybody have a question? Yes, sir?
If you were to ever just ask us to find the period, would you want it in a decimal value, or would you want it in a value of like 2 pi over 9.7?
Okay, so good question. So there's advantages and disadvantages to both. So what's the advantage to this right here?
It's an exact number.
Exact, right? That's an exact representation of the period. What's the disadvantage?
When you divide it by 4, it's not so pretty.
Okay. Well, okay, so no, you can just put a 4 at the bottom. That's all right.
Okay.
So what's the disadvantage to this? Yeah.
You don't know how long it takes. You just see it. You don't know how long it would take.
Exactly. We care about, so what is our period? Our period is number of seconds that it takes the ball to get around. So when you look at that number, do you have an idea of what I mean, initially you don't. You could sit there and do some mental math, right? But this, although it's not exact, you look at that and you say, oh, it's a little more than half a second, right? It's a little more than half a second it takes to get around the circle. So that's a big advantage to the decimal approximation, is it's just for making sense of what's happening, right? Of the time it takes to get around. The time it takes to get around. So it depends on the context in terms of which you should use, right? If it asks for an exact value, or you're going to calculate other values from it, it's better to use the exact.
Okay.
But if we're having a conversation about swinging this ball, and we want to make sense of the situation, then certainly if I'm swinging this ball and I say, hey, do you know that it takes me 2 pi over 9.7 seconds for this ball to get around, right? So you wouldn't say that, right? You'd say, it takes me about a little more than half a second, or 0.6 seconds to swing the ball around. Okay, so let's kind of summarize that here. Okay, so here's where we were before. We said the input into f is theta. And what was that theta? What did that mean? What does cosine receive? Everyone's going to write it either today or Monday. Eric. Okay, so the measure of the angle, so counterclockwise from the 3 o'clock position. It could be any angle measure. So we've used radians mostly, but it can be any unit of measure for angle. All right, so now, but then we changed it up and we said, let's look at this function as a function of t. And now the input of h is t. So we saw that it would be really helpful. We talked a lot about this 9.7t, because what does the 9.7t represent? What is that quantity then?
The angular speed.
No, 9.7t. The whole thing we're putting into cosine.
Theta?
That's like theta. That's an angle measure, right? That's an angle measure. So it would help to have a name for this. So they were trying to figure out a name. They went back and forth, and so then they ended up calling it the argument. Okay? So this thing that is what goes into cosine as a whole, we call the argument. Okay? The argument of the expression. And in this case, the argument, if it's the argument of cosine, that quantity, like we said, one more time, what quantity is it? Let's see. Sean, what quantity does the argument represent? Angle, oh, you got it, angle what? Angle's an object. We want the angle. What about the angle? It's measure, right? It's measure, so it's the measure of the angle. So counterclockwise and 3 o'clock. That's what the argument represents. Okay? And what's the meaning of the period? So the period of this function then would be, again, so does the period relate to t, the input, the argument, or the output? The input, the argument, or the output. What does the period a measure of? I'm hearing different things. He wants input. Input. It's a measure of the input. It's a measure of the input such that we get full cycle of output. Full cycle of output. And the way that we figure that out is we say the argument has to reach what? If the argument reaches 2 pi, we know that's the period of cosine. Then we want the t that makes the argument reach 2 pi. We need the t that makes the argument reach 2 pi. That will give us a full cycle. That's not us. That's last semester. Okay.
Mr. Ashbrook,
Yes? Period is interval of input that results in a full cycle of output. Interval of input that results in a full cycle of output. Okay, so let's do an example here. Okay, so a large Ferris wheel is rotating. The associated units are meters and minutes. Meters and minutes. A function related to this Ferris wheel is f of t equals 28 cosine 3t. So define each variable expression below as a quantity in relation to the Ferris wheel. So this is just like defining variables. So you can define variable expressions the same way that you define variables. So some of those are variables, some of them are variable expressions, some of those are just numbers, but all of those you can apply the 3 criteria for defining a variable to all of those. So that's what I want you to do. And then you got some follow-up questions, okay? So while I take a roll here, it's a really important exercise. So if the units are meters and minutes for a Ferris wheel and you have this function right there, what do all the parts mean? That's what we're getting at. What do all the parts of this expression, 28 cosine 3t, mean? So think of each one as a variable. You're going to So I should have said, in relation to a car on the Ferris wheel. That helps you a little bit. So you need to have a specific point on the Ferris wheel. So suppose you're riding it, the car you're in. So in relation to a car on the Ferris wheel. Is that what they call it? A car? A bucket? What is it? Cart. We'll call it a car.
Let's see.
I thought that question was it like if it was a normal ride or like a really quick ride?
Right.
Like, oh my gosh.
Yeah, I threw me off the second. I'm like, I don't know.
Good.
I stared at it for a second, and I was like, oh wait, not the
What was it, like 1.8 radians when it was 28 meters, right?
So he, like, flying.
Yeah, exactly. Yeah.
Yeah,
That's-
the wrong one. It would be like,
Well, yeah, so you had to understand radians to do that, right? Okay, Sarah, what did you put for T?
the time in minutes since the car left the 3 o'clock position.
How'd she do? Time in minutes since the car left 3 o'clock position. Is it a quantity? Is it specific enough? Does it have units? She nailed it. Okay, that's it. So what would 3T be? 3T. Riley, did you get 3T?
I got that as it's the argument and the measure of the angle theta.
Measure of the angle. Anything more?
It's to measure the angle after the time since the car started moving.
Okay, so yeah, you're trying to get that reference point. So what is our reference point? What's our starting angle? So angle starts from where?
The 3 o'clock.
Okay? And so I should say radians in minutes. But I'm assuming that you assumed that. Okay? I'm assuming that you assumed that. So what's the unit of this? Radians. Yeah, so if it's our argument into cosine, it has to be a measure of an angle. Swept counterclockwise from 3 o'clock. All right? So 3t is the measure of the angle from 3 o'clock. So then what does that make 3? What does that make the number 3? How would you define the number 3? The radians per minute the car is moving. Radians per minute. Danny?
It's not quantity, since it's a measurement. It's not an actual.
But we can still talk about it like the way we talk about variables, even though it stays constant.
Yeah.
We can still define it that way. So how will we define it? Yeah.
The measure of the angular speed of the Ferris wheel in radians per minute.
Okay, so that's what she said. So yeah, this is the radial speed. So radial speed means how many radians are swept per minute. How many radians are swept per minute? Okay, cool. So now, cosine of 3t. What do we think? Devin, what do you think? Cosine. What is cosine? What's the output of cosine? That's what we've been working on. It's always the same thing. What's the output of cosine? Not sure. Chad? Vertical distance above the horizontal diameter. What do we think? Is this vertical distance above the horizontal diameter? Cosine is horizontal distance right of vertical diameter. In? So what unit does this measure in? Fraction of a radius. So this is why we're pummeling this input-output thing, because when you see an expression that's cosine, or you see an expression that's sine, you'll know what it is. If you see a cosine, then that is a horizontal distance to the right of the vertical diameter, and it's going to measure in the fraction of a radius. Length. Okay, what is the 28? Danny thinks he knows this.
Wait, no, I have
Oh, good.
the
Yeah.
PT. So it doesn't matter what number you have inside the cosine, it's just always going to be either horizontal distance or vertical distance?
If it's a cosine, so what this number is a cosine. Okay, so that's what a cosine gives you. It'll give you a horizontal distance to the right in a fraction of a radius length. Every time in any situation, that's what a cosine gives. Okay, so we should write cars, horizontal distance, right? So the car's horizontal distance right of the vertical diameter of the wheel in fraction of a radius length. What is 28? What's 28? Christopher?
Is it the car's radius to the center of the circle?
Okay. Okay, so it's distance from the wheel center to the car in radius length? No, this is in meters, right? This would be in meters. This is a huge Ferris wheel, but there are some that are this big, right? 28 meters. That's like, what is that like? It's like an 8-story building, right? It's a huge Ferris wheel, but there are many in the world like this. Okay. So that's the distance from the wheel center. So this is the radius. This is basically the radius length in meters. How are you doing now that we're putting how are your answers compared to these? This is how good you need to be. This is the level of understanding and precision you have to have if you really understand what's going on. Okay, so then what's 28 cosine 3t? What's 28 cosine 3t? James, what's that? Okay, well, what's a cosine? Tell me what any cosine is. What does a cosine give you? Horizontal distance to the right. Horizontal distance to the right of the vertical diameter. We're going to multiply that by 28. So what would that be? BJ, 28 cosine 3t. Okay. Okay. In what unit? In radius lengths. Car's horizontal distance to the right of wheels vertical diameter. So what would it be if it were just in radius lengths? What would it be? Or in fraction of a radius? That would just be cosine, but now we're multiplying by 28. So we're taking that fraction of 28. So that gives us how many meters? Right? So that's what cosine does. When you multiply that cosine times the length of the radius in your distance unit, then you're taking that fraction of the radius. We're taking that fraction cosine of 28 meters. So we're going to get how many meters to the right the car is. Okay, what's the input? Which of these above is the input to the function? Of all those things we just defined. Okay, I heard t, I heard 3t. To the function. The input of the function is t. What's the output of the function? Which one of those things? Which one of these things is the output of the function? Cosine 3t is the output. No, the whole thing, right? 28 cosine 3t. Okay, what's the argument? That's 3t. Okay, did you find the period of the function? How do you find the period of the function? Aiden. And how do you do? Good. How do you do that? That's right. What's it? So set what equal to 2 pi? And what's the angle? What's that? 3t. Is 3t the angle? Yeah, 3t is the angle. So we want the time period such that that angle, 3t, reaches 2 pi, because we know that angle is going to make a full rotation. So what is the period? T equals?
2.09.
What you got from 2 pi over 3. And you said that's about? 2.094 units? Minutes. Does it make sense for a huge Ferris wheel? Does it sound reasonable for a huge Ferris wheel? Yeah, it'd take you about 2 minutes to get all the way around. It was moving pretty good. Okay? Definition of period. We've done it many times. What is it? Is it to have to do with the input, the argument, or the output? Period. Input. It's the interval of input that results in one cycle of output. Okay, so now how do we graph this? So what do we say? We'll first look at what was our period? 2.094. So that's right about here. This is 2, right? This is 2. This is 1 and 0. Okay, so right there at 2.094 minutes. So now we're going to sketch the curve ourselves, okay? So what do we need on this horizontal axis to be able to do that well? So I've got 2.094 is going to be how long it takes for one full cycle. What else am I going to need on this horizontal axis? Alexis, what should I do with that 2.094 to give us some more reference points here? Divide by 4, okay? And what do you get when you divide by 4? 0.52? 0.502?
0.523.
That's too big. 0.52 is not going to, times 4 is going to be 2.094. Sure it's not 0.502?
Positive. 0.52.
Oh, right, because 2 is in the hundredths place. Sorry. Okay, right. My fault. Okay, so 0.52. What else? So that's going to be helpful. That's 1/4 of the cycle. Then what? You can divide this by 2 or multiply this by 2. What will we get? 1.04. And then you could take 3/4 of that, or you could add a half plus a quarter. You could add these two, or take 3/4 of that. And what do you get? 1.56. So that gives us these critical quarter points of the first period. Okay, what about this way? So we're sketching this function. What is it? What is the output of the function giving us again? Car's horizontal distance to the right of the Ferris wheel in meters. So now we got to think about maximum and minimum. So if we're going to sketch this, so what's the maximum meters to the right? What's the maximum meters to the left? 28. And at time 0, where is the car relative to the vertical diameter? Is it at the max? Is it at the center? Is it at the vertical diameter, or is it at the min? So what point should I grab? 0, 28. Why? Because at the 3 o'clock position, it's its full 28 meters to the right of the vertical diameter. And what happens in that first quarter cycle? It goes from 28 meters to top of the circle. Horizontal distance is? Alex, top of the circle. Horizontal distance is what? 0. So what will the graph look like? Start here and straight like this, straight line? Yes, remember it says, so we came up with something like that. We worked that out a week or so ago. Worked out why it's concave down, right? Because the changes are getting more negative. With each time it goes, changes get more negative, so the rate of change is decreasing, getting more negative. Okay, then the second quarter circle. Here we are at the top. The horizontal distance goes from what to what? Horizontal distance goes from 0 to negative 28. So at halfway in the cycle, we're at negative 28. And then from there, it goes from negative 28 to, at the bottom of the circle, the horizontal position is 0. And then in the last quarter cycle, 0 back to positive 28. Where's that? It's my best guess. Okay. Does it stop there? No. If we keep riding, then it does another cycle again. So from 2 pi to 4 pi, we get the exact same cycle of output values. So this would keep going. So let's check our work. Moment of truth, right? What pretty color do you want? Blue. Oh, that's light blue. How do we do? Perfect, okay? Questions on this example? Anybody have a question? The natives are restless. Tension level is low. Here we go. So you need a task. Okay, so here's a new one. A water wheel makes a full rotation every 13 seconds. The radius of the wheel is 7.5 feet. The bottom of the wheel is 2 feet above the surface of the water. For whatever reason. Maybe the water, so usually it scoops up water at the bottom. Maybe the water level dropped because of a leak in the tank or something, or a drought, okay? Anyway, so now the wheel is sitting up above the water. 2 feet above the surface of the water is the bottom of the wheel. Okay, so point on the wheel starts at the 3 o'clock position and turns counterclockwise. So you've got 4 functions to write, starting with the first. Read carefully. Think about what quantities it's telling you and how you're going to form these functions. So this is a real good test to see if you know what's going on. Okay, so you're going to write a function f in number 1. You're going to write a function g, then h, and then j. Read carefully. Really know what quantities this is talking about. Okay, in my past experience, most students get number 1 wrong. So who knows what's going on? Show me your number 1. Nope. Oh, we got it. Good job. Show me your number 1. Good. Nope. Nope. Read what quantities it's talking about. Nope. Read what quantities it is. Think about what you're learning. Not it. Number 1. You got it. Nope. What's the input? What's the output? Nope. Okay, so the input is measure of the angle, swept by the point. The output is the vertical height above the horizontal diameter as a fraction of a radius length. Ashley, what function is that?
F of theta equals sine theta.
She wants f of theta equals sine theta. How'd she do? Is the input of sine the measure of the angle, swept counterclockwise from 3 o'clock? Is the output of sine the vertical height above the horizontal diameter and a fraction of a radius length? That's it. That's the function f. Sine theta. That's what it's talking about. It's the same input and output that we've been hammering the last week. It has nothing to do with all these numbers that you're given, right? Because it's talking about angle swept in radius, and height above horizontal diameter in fraction of a radius. That's what sine is. Okay, what about g now? What's the input into g? Still theta, but what's the output now? It's vertical distance, but in what unit? In meters, or in feet. So this gives us a fraction of how many feet we want, or of what number? Yeah, so if 7.5 is the radius, we want that fraction, sine theta, that fraction of 7.5 to give us feet above. Sine theta gives us the fraction that we want of the full radius, 7.5 feet. We good? H. What's the input into h? As a function of Now time elapsed. What's the output? In feet. So do we have the 7.5 or not? So we got 7.5, and it's still vertical distance, so sine. So now we need to figure out what the radial speed is, right? So it makes a full rotation every 13 seconds. So how many radians every 1 second? How many radians every 1 second if it makes a full rotation every 13 seconds? So here's a way to do it. So we have this unknown, b. Call it b. When t is 13, what is b times 13? So 13 is our period. So it's giving you the period. So we need b times our period 13 to reach 2 pi. That's another way to think of it. And so b is that. Therefore, that coefficient is 2 pi over 13. Okay, we'll pick it up here on Monday.